For what we have in the case of number 4, okay, we have y prime minus 9x squared y is equal to 0. And just for the sake of brevity, just applying the series terms for y prime as well as y. If you notice, okay, we have the series from y prime, c1, 2c2x, 3c3x squared, and so on. Now, if I distribute negative 9x squared over y, I'll come out to these various terms, and if I combine like degree terms, okay, we're going to have just c1 as the standalone constant, and the only first degree term that we have will be 2c2x. And since we don't have any other constant to combine with c of 1, that is going to go out. And as for what we have in terms of first order terms in x, we have only 2c2 as a coefficient. And since there's nothing else to pair up c of 2 with, okay, this will become negligible. And we're going to have that c of 1. If you notice, the next time that c1 appears is with 4c4. And since this is 0 and we have no other x cubed term to pair up with c of 4, since c of 1 is negligible, c of 1 is equal to c of 4. And you will have going up every 3 units in the subscripted terms. You will have c of 1 is equal to c of 4 is equal to c of 7 is equal to c of 10. That would become negligible. Same thing is going to await c of 2. If I were to go up every 3 units, there you have like 5c of 5 minus 0. c of 5 would go to 0. That is equal to c of 8, c of 11, and so on. And we have this equal to 0. Now, where we have the non-negligible pairings to occur, we have 3c of 3 minus 9c of naught is equal to 0. And if I put c of 3 in terms of c naught, so I have c of 3 is equal to 9/3 of c naught. And we'll say that we have 3 over 1 c naught So I'll say that I have 3c naught over 1 factorial. So far, so good. And then next I have 6c of 6 minus 9c of 3 is equal to 0. And here I have c of 6 is equal to 9/6 of c3. And condensing, I have 3/2 c of 3, and with c of 3 at 3 over 1 c naught. So I'm going to have 3 squared over 2 c naught, and right now I have 3 squared over 2 factorial c naught. And if I were to go out even further, I have 9c of 6 make that 9c of 9 minus 9c of 6 is equal to 0. So I have c of 9 is equal to 9 over 9 c of 6. And if I just put this in terms of 3, so we have 3/3 of c of 6. So I'm going to have what's going to be 3 cubed c naught over 6, and there's going to be a flowing pattern. Okay, so you have 3 cubed over 3 factorial c naught. And if you notice, okay, for the pattern, we have c of n. Notice the degrees and the values that we're taking the factorials of. You're going to have to be 1/3 the subscripted value. So right now we have c of n is equal to 3 to the n over 3, and we have all over n/3 factorial c naught. And to make an adjustment, say if I want to get rid of the fractions, I can just let n be equal to 3k So for c of n, I say that I have c to the 3k, and we have is equal to 3 to the 3k over 3. So this would be k, and we have all over k factorial c naught. And applying what I have for the general solution, there we go. All right, so if I let n be equal to 3k, it will have transforming. Okay, so we have at the base. Okay, so I'm going to switch out the variable n for k. And again, we have with c of n. Okay, this would be c of 3k, and x of n will become x to the 3k. And filling in, and I'm just going to go ahead and extract the constant. So we have c naught times the summation as k goes from 0 to infinity. Now I have of 3 to the k times x to the 3k all over k factorial. And if I condense together, what's going to happen? So we got c naught times the summation as k goes from 0 to infinity. And I can go ahead and compile together in the power of k. So I have 3 to the k power. And notice that we have for x to the 3k, if I think of the power property, you see we have x cubed to the k. So for what we have upon condensing, so you have c naught times the summation as k goes from 0 to infinity. And we have of 3x cubed to the k power over k factorial. And guess what? This is one form of what we have with e to the x, where we have x projected out to 3x cubed. So we have for the solution, we have a constant times e to the 3x cubed.